going to start chapter 9 by revisiting something we did back with the trig stuff, and that's circles. So a lot of this stuff's going to kind of be similar to the stuff you've already done before, just a little more background to it. So first up, what is a circle? So I've got a point drawn here, and we'll call it HK. I'll explain more about the significance of HK in a moment. But think about what is a circle relative to this point? And you should be thinking about something along these lines. It's all the points that are the same distance from some center point. So if this is the center point, I'm looking at all the points I could ever make that would be the same distance from that. So something like that. Now, a question I'll throw out there, how many points are there on a circle? Well, there should be an infinite number of points that could fit that definition. They could be the same distance from that center point. There should be, between any two of these I picked, there should be a whole bunch more. And in between any of those, there should be a whole bunch more. And in fact, there should be an infinite number of points between any 2 points. So there's a lot of points that could make this true. For all the shapes in this chapter, HK is a central point to the shape. So for a circle, this would make sense. This is the center point of the circle. So we're going to call the center point HK. Now, if you choose any of these blue dots, doesn't matter which one it is some XY coordinate. But it's a particular XY coordinate that is the same distance from HK no matter where you go. And we call that distance it is from the center the radius. So these should be familiar terms to you. Now this is going to look really similar to what you did back in chapter 4 when we were doing the unit circle. Because if that radius is a specific distance from the center, it's always going to be the same amount. So we should be able to use distance formula using those points to define that radius. So now how far over do you go? Well, whatever this change in x is, delta means change. That's something you'll start seeing a lot more moving into calculus and physics. You'll probably see it in chemistry too. This change in the y direction, we'll call that delta y. So whatever the change in x is squared plus the change in y squared, that's going to be our distance formula. So let's look at how we can define that. Well, the change from this center point to this x coordinate would be, we'll call it x minus h squared. You could call it h minus x squared, it really doesn't matter, but this is the typical format you'll see. And then to go from k to y, let's call it y minus k squared. And that should look pretty familiar. That's the circle definition we played around with a little bit before. This time I'm putting an h and a k in there. It's a little bit different symbols, but it's the same idea. And it is just Pythagorean theorem. I want you to really notice that. You got the radius squared, you got the change in x squared, change in y squared, but it's really just Pythagorean theorem. Pythagorean theorem defines a circle. If you visit my website for the notes section, there's quite a few Desmos models and animations you can play with here. Pretty much every section throughout this whole chapter has got some models to mess around with. So first up, circles. If you pull that up, here's what it looks like. And it's going to give you a circle using this definition that you can play around with. H and K, we said, was change the center point. So if you mess with H and K, that's going to change where the center is. K raises it up and down. R is the radius of that circle. So the bigger I make it, the longer R is. And I've got a point on here that you can play around. You can drag it around. Right. So I've got it set where it shows you the x, y coordinates. If you come down a little bit more, here's sort of the significance of those. So the idea is, the definition of a circle, it's all the points that would be the same distance from some center point. So this just shows you what the x, the y coordinates are, and shows you that the distance doesn't change no matter where I go. So if you just kind of drag that around, you can verify that. You'll see that x and y coordinates change, but this radius distance never changes. And I just used different variables because I already had x, y, and r taken, so I used p, q, and d. For a few examples here, the first one, we're going to take the definition of a circle and we're going to apply the center point and diameter. And I'm using diameter, not radius. We're going to apply all this and put it in the circle definition to write the equation. So let me start with that equation again. R squared equals x minus h squared plus y minus k squared. Now diameter is 5, so I'm going to make a note. The radius is going to be 5 halves. And I do want to make it a fraction. You'll see as we go throughout the chapter, fractions are way easier to work with than the decimals with the work you're going to need to do. So we'll keep it a fraction. All right, well, r squared, that's going to be 5/2 squared. And that's going to equal x minus your h coordinate. So x minus -4 is going to be x plus 4. That's squared. Plus y minus that y coordinate for the center point squared. And as far as making a definition here, you can leave these as they are. We typically do. You do want to take the radius and go ahead and work it out. But I wouldn't expand the x plus h or x plus 4 or the y minus 2. I would leave them like they are, because when you get it in this format, you can easily take your center point and get it from the h and the k there. So that's good enough. That'll be your equation. That's where you'll want to leave it. Now, something you're going to do quite a bit in this chapter is you'll get an equation sort of like this, and you'll need to write it in the standard form. Now, we're just starting off with circles. We're going to learn 3 other shapes, and you're going to need to be able to look at the equation. And by the time you're done with all these sections, you will be able to literally look at this equation without doing any work. And in a matter of probably a couple seconds or less, you'll know which shape it's going to make. But the process is always going to be the same. And this is getting back to chapter 2. We're going to need to complete the square to work this thing out. Because if you think about the format of a circle, let me just jump back real quick here. If you look at the format of a circle, you want these things to be perfect square binomials. So if we jump ahead back to this problem, we've got some pieces that look like they could make some perfect square binomials, because you've got x squared and x, y squared and y. We just need to make that happen. And then we want to take any constants and get them over to the other side. So that's the reason we want to use completing the square. So back in chapter 2, when a lot of y'all were asking, can I use this? You didn't really realize it was calculus, but it was a calculus definition for the vertex of a parabola. And I kept telling y'all, now I really need you to learn completing the square now, because it's going to really pay off later. Well, this is where it's going to pay off. So let's go through the process. Completing the square, I want to keep my x's together, I want to keep my y's together, and I want to take my constant and put it over there. So I'm going to do x squared minus 6x, and this is the way I like to do it. I like to go ahead and kind of get a parenthesis ready to go, kind of spaced out so it's going to look like a trinomial. Same thing for the y squared minus 2y. Leave some space right there because something's going to fill it. And then I'm going to subtract that 6 and move it over here. Just like with parabolas, if there was a number in front of x squared or y squared, you need to factor that out. Of both x terms, both y terms. Factor that right away. That's always going to be the case. I don't think you're going to see that much for circles, but you will definitely see it soon for some of the other shapes. All right, the process was take half of this. You don't have to worry about the x. Just take this number right here in the middle, half of it, and square it. So half of 6 is 3. We square it, we get 9. You don't have to worry about the sign, because when you square it, it's going to be positive anyway. Now, you made that up. That 9 was not there. You put it there to make this work out nicer, which is fine as long as you put it over there too. And here we're going to take half of 2, which is 1, and square it, so that's going to be 1. Again, I made that up. It wasn't there already, so as long as I put it over there, we're good to go. And now we can kind of reduce it down. We should be done really soon. So x minus 3 squared. You can factor, but the trick is it's x minus half of this. Half of this number happened twice when you FOIL it out, and it got squared to make that number. If you need to factor, you'll see all that happen. Y minus 1 squared. And in the end, it's going to equal 10 minus 6, so 4. And that'll do it. That'll be your equation for a circle that fits this definition, or fits this equation. Something else that's going to come up on the homework is finding the x and y intercepts of some of these shapes. The process is the same as it's been since pre-algebra. If you want to find y-intercepts, plug in 0 for x. If you want x-intercepts, plug in 0 for y. The process isn't going to change. What I recommend here is just do a little simple sketch. It doesn't have to be perfect. Let's just get a sense of what this thing's going to have. How many x-intercepts, how many y's? It could have 2 of each. It could have none. So we'll have 4 for the x. We'll have 2 for the y. We're going to have a radius of 4, so it's going to come down to here, it's going to come over to here, And even though I can kind of see where the y-intercept's going to be, I really want to do this mathematically. But at least I know what, I've got a good idea, I can check that. It should be 2 for the y-intercept. X-intercept looks like it's going to be somewhere between 0 and 1. And it looks like there's going to be another one over here, probably around 7, something like that. So I've got a sketch, I've got an idea. I'm going to start with that y-intercept because I'm pretty confident it's a 2. And I think I can check that pretty easy. So this coordinate right here, I'm pretty sure it's 2, but it's definitely going to be 0 for the x. So we'll put in 0 for x, and that's going to give me -4 squared. So this is the y-intercept. So -4 squared plus y minus 2 squared equals 16. So that's 16. For now, I'm going to go ahead and leave this like it is. You could expand it, but I'm just kind of looking at what's happening. These 16s are going to cancel out, and I don't think I'm really going to need to expand that. I think it's going to make it more work in the end. So if we subtract these 16s from both sides, that's going to give me 0. If you square 0, you're still adding 0. So that confirms it. Your y-intercept is at 2. So now onto the x-intercept. And again, I think it's between 0 and 1, and I think it's between 7 and 8. Because that's 0 for the x, that's 8 for the x right there. So let's see how that unfolds. So if I want to know the zeros, I don't know the x-coordinate, but I know that the y-coordinate has to be 0 on both of those. So x minus 4 squared. And we'll show that this is the x-intercept. X minus 4 squared plus 0 for y, so -2 squared, equals 16. Okay. So same deal here. I'm going to leave that as is. Go ahead and start filling this out. So x minus 4 squared equals 12. All right, I'm going to take a square root of both sides. So here's where you got to be careful. You took a square root, so it's plus or minus. Square root of 12, if you need to do the breakdown, you can. It's 4 times 3, 4 is a couple of 2s, so it's 2 square root of 3. And finally, we're going to add the 4 to both sides. So 4 plus or minus 2 square root of 3. If you want to try to confirm that to see if it is around between 0 and 1 and 7 and 8, you can. But it's looking pretty good. That should be good to go. So there's your y-intercept, there's your x-intercepts.